Good day. This is a video on computational geometry, part of the series of videos on advanced algorithms. In this video, we're going to look at an example of a sweep line algorithm. I will present the problem and then I will present an algorithm and a design process that leads to that algorithm. So here's the problem. The input of the problem is a set of intervals in 2 dimensions. And the intervals are parallel to the x-axis, and each interval is given by 3 numbers. First is the y-coordinate, where on the y-coordinate is the interval, for example 2, and then the x interval. So this interval starts at 1 and ends at 8. And I choose to have these intervals half open. So it starts at 1 and includes 7 but not 8. So that's the input, the set of such intervals. What we want to compute is something we call a top surface, which is again a set of intervals, exactly the same format as the input, but that represents the topmost surface of these intervals. More formally, the intervals in the output, which we denote by t, cover exactly the same coordinates on the x-axis as the set S. So the union of x intervals from the input set S is exactly equal to the union of x intervals from the output set T. In addition, what we want is that for each interval in the output, we have the y value of that interval to be the maximum of the y values of the intervals that from the input that this interval from the output covers. So here is let's first draw the example here and we'll see what we mean. So the output intervals will look like this. Here I draw them in blue and in dashes. So this is the output, the top surface of this set of intervals. So it's quite intuitive what I mean. As you can see, the blue intervals cover exactly the same span on the x-coordinates as the input intervals, condition 1, and condition 2 says that for any of the blue intervals, if we look at any of the x-coordinates in that interval, then the y, we can guarantee that the y value of this interval is equal to the max of yj's of all the intervals that cover this x. So in this case, if I take this point, I see that these 2 intervals from the input cover this point, and the max of 3 and 2 is 3. So the yi of t is 3, and the same yi of t should hold for all the points in this interval. So it's a little bit complex to express it formally, but it's very intuitive what we mean. You can see from the picture what we want to compute. In addition, we require that the interval endpoints in T are from the set of endpoints in S, so we do not want to create artificial intervals here. For example, chop this interval into smaller intervals. So here is the output written out in this format, and you can stop the video and see that this actually corresponds to the picture. So that's the problem. How do we solve it? Well, one approach would be some sort of brute force algorithm that, let's say a nested loop algorithm that takes each interval from the input and compares it with all the other intervals from the output and see whether they cover it, so overlap with it, and have larger y values than it. And in this way, we could see if any part of this input interval should belong to the output. If yes, we put it to the output. And so in this way, we would, running through all the intervals, we would be able to construct an output in time that would be at least n squared, depending on how we implement that. So that's the running time of the brute force algorithm. That does not take into account this geometric property of the problem. So instead, we will try to devise a sweep line algorithm. So let's look how we do that. So to design any sweep line algorithm, one first has to decide how the line will sweep through the space. It's not so important in which direction here, but it's important to decide whether we will sweep according to the x-coordinate or the y-coordinate, because they play different roles in this problem. So here it is natural to sweep along the x-coordinate and then build up the output as we go from the left to right. And then three kind of data sets are usually maintained in the algorithm, a sweep line algorithm. The first data set is the data set of events. So when do we have to update our sweep line status? When does the status change significantly? So in this case, it seems that the events are the start and end coordinates of the intervals in the x direction. So we can have the events in advance, we can sort them according to the x coordinate. Then the next data set that we need to maintain is the sweep line status data set. So in this case, it's natural to have the sweep line status data set as the data set of intervals that intersect the vertical sweep line as the algorithm progresses. So for example, at this point, these two intervals should be in the sweep line data set. And finally, we will have a data set that we construct the output. So sometimes the sweep line algorithm may not have this data set because the output is just one bit, like we had in the example of a line intersection in the algorithm, which finds whether there exists an intersection in the set of two-dimensional line segments. There, the output is just one bit, so then there is no need for this data set. Here we have to somehow maintain that in this algorithm. So then we have to think exactly how do we update these different data sets, what kind of operations we want to perform on these data sets, And based on the operations and how many times we do these operations in the algorithm, we choose the appropriate data structures to maintain these data sets. So we know that the events we know in advance, we can sort them, we can have them in an array or in a list. Now we have to look a little bit deeper how we update the sweep line status. So there are two kinds of events. There are start points of intervals and there are end points of intervals. And we want to think what do we have to do with a sweep line data set and with the sweep line status data set and with the output under construction. So when the event is the start point, obviously we want to insert the interval into our sweep line status, and then we want to check whether it is the topmost interval in the y direction. So it seems that we want to organize our intervals in the sweep line status according to their y coordinate. And so when we insert a new interval, we want to check if this is now the topmost interval, then we need to append a new element to the output under construction. And then possibly update the last existing interval in the output to show that now this interval ends here, and now we insert a new interval, this one. If the interval is not the topmost, we just insert it into the sweep line status and we do not have to update our output, like in the case of this interval. If the event is the endpoint of the interval, then we need to find this interval in the sweep line status and delete it from the sweep line status. And then again, we want to look at what kind of interval we had. So if we deleted the topmost interval, like in this case, at this event, then we want to look into the sweep line status. If there is sweep line status now is not empty, we take the topmost again interval in the sweep line status, and then we insert it at the end, append it at the end of our output with the new starting time, which is equal to the ending time of the interval that we just deleted. But obviously, if we delete an interval that was not the topmost, we just delete it from the sweep line status and we do not have to update anything. So now that we know what kind of operations we do on this data set, we can choose an efficient data structure. So we can see that here to the output, it looks like we just append intervals to the end of the output. So this could be a simple array or a linked list. But for the sweep line status, we want to efficiently insert into it. We want to efficiently find the topmost, given the y order of the intervals. We want to find and delete intervals from the status. So for these kind of operations, if we want to have efficient implementations of these operations, it seems that a red-black tree or any other balanced binary search tree ordered according to the y coordinate would be a good choice. So now let's put this all together into a sweep line algorithm. So here is the pseudocode of the algorithm for computing the top surface of a set of intervals S. As we sketched out on the previous whiteboard, we first define what are the events. So let E be an array of endpoints with a field X to represent the X coordinate of the endpoint from the input array, together with the associated point pointers to the intervals, to the corresponding intervals. So there are two fields in each element of the array E, the actual x-coordinate of the event plus the pointer to the interval that corresponds to this beginning or the ending point of the interval. So the size of this is twice the size of S. Then we sort E on X. Then we create a red-black tree and call it L. So this is the sweep line status data structure, initially empty. And then we create an empty list, which is our empty list T. And this is our output that we are constructing. Then we go through the events in the X order. So from P equals from 1 to the number of events. We have two cases. Either this is a starting point or else it's an ending point of an interval. If it's a starting point, we insert the interval into the sweep line status data structure L, and then we check if this whether this is a now the topmost interval in the sweep line status or not. If it's not the topmost interval, like for this case, we don't have to do anything. If it is now the topmost interval in the event in the sweep line status, like for this interval, when we insert this interval, it becomes the new topmost interval, then we have to see if before inserting this event into the sweep line status, the sweep line status was not empty. Like in this case, it was not empty. Then what we have to do is we have to take the last interval from the output and set its endpoint to be equal to the beginning of the new topmost interval. So we had this interval in our as the last element in T. Now we crop it and set its endpoint to be equal to the beginning point of this new topmost interval. But of course we don't have to do this step if the sweep line status was empty, like when we processing this event, sweep line status was empty. So now when we insert this new topmost interval, the size becomes equal. The size of the sweep line status is exactly equal to 1, and then we don't have to do this step. In any case, when we have a new topmost interval, we append that interval to T. So it will be in the output. To process the endpoint event, we delete it from the sweep line status. And then, in a lot of cases, we don't have to do anything else. Like for this interval, if we delete it, we don't have to do anything else. For this interval, if we delete it, we don't have to do anything else. It is already in T, so it just stays there. When we have to do something is when the interval that we have deleted was the topmost one, and then there was something below it. So it's the topmost one. Here I compare the y-coordinates of T last and the y-coordinate of the interval that I just deleted from the sweep line status. If they are equal, I know that this was the topmost element. You can also do the check before this, a more direct check. And then if the size now after deletion is larger than 0, so for example we deleted this, then there is still something in the sweep line status, then what I do is I append this new topmost element, which is this interval, to T, but of course I have to adjust its starting time, starting x-coordinate. It should be equal exactly to the ending x-coordinate of the interval that I have just deleted. That's what I do in this line. So that allows us to compute the output t after we have processed all the events. So what is the running time of this algorithm? We can see that here we do sorting on the array of size 2s, and then we process 2 times s a number of events, and processing each of these events, we do some constant number of insert, delete, find maximum operations in the red-black tree, all of which take logarithmic time. In the worst case, there can be n intervals in the sweep line status, so all of these in the worst case take log n time, and these append, they take constant time. So all in all, this loop takes n times log n to process if there are n intervals, and this also takes n log n. So all in all, the running time is n log n, which is better than the best we could hope for this naive approach, which was n squared. So now you can think about some special cases. I was not handling these special cases when maybe some intervals overlap, so they have the same y coordinate and overlapping x intervals. Maybe there are some intervals that start and end at the same x coordinate. How do we have to modify this? Maybe the sorting, you have to break ties somehow. This search in the red-black tree, so that this works for all of these other cases. You can think about that.